Welcome back. It's now time to get into some nitty-gritty on some of these definitions again. Of course, we've kind of seen some of these already in earlier questions, but now let's put a definition to it. So you may have noticed that the four-dimensional gradient operator, partial over partial x to the mu, functions like a covariant four-vector. In fact, it is often written as partial mu for short. For instance, the continuity equation, which we saw earlier for sure, is partial mu j mu equals 0. Has the same form of the invariant product of two vectors. Okay? The corresponding contravariant gradient would be partial to the mu is equivalent to partial over partial x subscript mu. We want to show or prove that the contravariant derivative acting on phi is a contravariant four-vector if phi is a scalar function by working out its transformation law and using the chain rule. So it sounds like we're going to have a gruesome question as far as handling details and handling the grittiness of it, but if we just take it one step at a time, we should be all right. All right, so first and foremost, if we're trying to use the transformation law and the chain rule, let's be careful on how we write everything out. That being said, the zeroth component for some scalar function phi, if we transform this, this tells us that we need the partial of the zeroth component of the covariant vector, in this case the covariant four vector for position, acting on phi. However, we can write this to the normal form of what we know we need at the cost of a minus sign in the contravariant form for the vectors that we need. So this being said, now we see that the zeroth component needs to go to negative c t bar acting on phi. So in actuality, this transformed zeroth component is negative 1 over c d by dt bar phi. Okay. Again, what we see here is that we need to be careful with a lot of things, including the chain rule acting on phi and t bar. That being said, if we write this out, we get a negative 1 over c, and as you see, the t bar needs to act on phi here, t, and then t, and then the derivative of t goes to t bar. But then we also have the chain rule with respect to the position, because we don't know how that acts on t bar, and y acting on t bar, z acting on t bar. So we get quite a bit to deal with here. And so what we know is that from the inverse Lorentz transformation, dt by dt bar is equal to gamma, dx by dt bar is equal to gamma v, and then similarly we get 0 and 0. Therefore, when we plug them all in, you see that we get a 0, 0 there, cancel that down, and we're left with a gamma in both, so we factor that out. And then we see we just have the time, the temporal side derivative of the phi, and we have a velocity with a positional side. So pretty standard, I would say, with what we expect in these kind of transformations. And now what we're trying to do is trying to force factor everything back in after we already show, or distribute everything back in after we show that the chain rule leads to these factors of gamma and gamma v. So when we do that, we put this negative 1 over c back into the derivative form, and we can write the negative v over c term here. So be aware of two negatives, v over c, v over c. This goes in there, this goes to beta, and we see that x is the first term, so, or with the one component. So tidy this up. Again, be careful because the negative sign only goes back from the contravariant to the covariant. So we're good there. We don't need the negative sign on this one. Negative beta does stay though because spatial domains stay. And we see that in general we get gamma is that the derivative bar for the zeroth component goes to the zeroth derivative of phi minus beta, the ordinate first ordinate of phi as well. So that transforms like we expect. And then for the last stuff, we have for lambda, or for mu equal 1, 2, or 3, just the spatial parts now. We already took care of the temporal part. We have partial 1 to the phi, and we just break that down like we did last time. Again, we see we're going to have a chain rule event, so we have to get to d bar or x bar via t, x bar via x, x bar via y, and z, and so on and so forth. Using the coordinate or the transformation rules, we see what factors get a gamma or a gamma v over c squared, things like that. And then we can do the factor, refactor technique again, rewrite all the coordinates, and we see that we boil down to, again, if we want the one component, we get gamma, partial 1 phi minus beta, partial 0 phi. So again, these are transforming kind of like we expect. Now, if we want the y and z term, well, of course, we know that those transform to the same thing. Y bar goes to y, z bar goes to z. So these two are certified in that respect as well. So that's actually really cool. So what we can say is that in conclusion, the contravariant vector, gradient vector, gradient 4 vector, transforms the same way as a contravariant vector does under the Lorentz transformation. So it is a contravariant 4 vector. So that being said, pretty cool stuff. Of course, these definitions get used over and over and over again. So it's just a pain to deal with. Again, some authors have the other order. Find out what they describe it as, and then move on. With that being said, if you can get used to this stuff, it's going to help you a lot later on. So definitely worth the investment in it.